Chapter 8 was the last chapter of Unit 2, and we introduced the concept of polarity, both bond polarity and molecular polarity, ultimately to help us answer the question, why do some molecules smell where others don't? The first activity that we looked at was a station activity where there were different liquids set up around the room in burettes, and you had a charged wand, and you charged the wand by rubbing it on the rabbit fur, and then you brought the wand near the different liquids, and you saw different responses to the charged wand from the different liquids. Some of the liquids bent towards the charged wand, some of them had no effect. The other thing you tried was putting a drop of the liquid onto wax paper and observing that some of the liquid formed a really nice round bead, where some of them did not and just formed this flat sort of a puddle on the wax paper. And after we did that, we related our observations to something called polarity. And polarity is, if we're calling a molecule polar, we're essentially saying that the molecule has one end that's more positive and one end that's more negative. That's all it means. So for example, water is a polar molecule, meaning one end is more positive, would be this end, and one end is more negative. Methyl alcohol or methanol would be another example of a molecule that is polar, where one end is more positive and one end would be more negative, the oxygen end there. Ethane, as an example, or CCl4 or BF3 would be examples of nonpolar molecules, because those molecules don't have one end that's more positive or one end that's more negative. There is no charged end associated with those molecules, hence the term nonpolar. Now, what we really attempted to do afterwards was say how the liquids that attracted to the charged wand must have been polar. If the charged wand had a charge, whether it was positive or negative, the only molecules that would have attracted themselves towards the wand would be those that have a charge, hence polar. The liquid that didn't do anything in the presence of the charged wand would have been nonpolar. There were no charged ends of the molecule that would have been attracted to the charged wand. We also use the idea of polar molecules to explain whether or not the liquid would bead up on wax paper or turn into a flat puddle. If the liquid formed the round bead on wax paper, then those molecules were most likely to be polar, because their positive and negative ends would link up and cause them to have really strong, what we will later define as intermolecular forces of attraction, meaning the molecules are held together really strongly and really closely together. Nonpolar molecules that lack a positive and negative end do not have strong intermolecular forces of attraction, so they don't hold themselves to each other strongly or tightly, so they will spread more on the wax paper like we saw. We use the concept of polarity to introduce the term or the phrase like dissolves like. And this is a shortcut for helping us determine whether or not something will dissolve in another substance or whether they will be miscible. And the main solvent we looked at all year was water. We looked at examples of water and oil versus water and sugar or water and salt. Water is a polar molecule like we saw up above. Only other polar molecules will dissolve in water. So if it's a polar molecule or even something ionic, even though ionic things are not covalently bonded, we can consider ionic things to be polar because there's a positive ion and negative ion. If it's nonpolar, it's not going to dissolve in water or anything else that's polar for that matter. And the reason being is that if something is polar and we introduce something that's nonpolar into it, like the example of water and oil here, the oil molecules, being nonpolar, don't have a positive or negative end, so there's nothing to attach themselves or attract themselves to the water molecules. In other words, the water molecules are really strongly attracted to themselves by their positive and negative ends linking up, that they're not concerned with trying to attract to the oil. There's no positive or negative ends in the oil molecule for the water to attract to. So nonpolar will dissolve in nonpolar, polar will dissolve in polar, and it has to do with whether or not they have positive and negative ends of their molecules. I gave you an image here because we did an example very similar to this in class. I used water and hexane, but the idea is similar, that these two liquids are immiscible. We can see the line, the interface between the two liquids, and then dissolving iodine doesn't dissolve in the water. It only dissolves in the nonpolar liquid because iodine is nonpolar, where sugar, which is polar, will dissolve in the polar substance. So we can see that there. We did not classify intermolecular forces based on their specific types. Like, we didn't use the term London dispersion, but we did look at relative strength of intermolecular forces. So, for example, these chlorine molecules, these diatomic chlorine molecules, which are nonpolar, they don't have positive or negative ends to them, are weakly attracted to each other. So here's a covalent bond between them, right? That was the sharing of electrons. We looked at that in chapter 6 and 7. What we're introducing now, or what these red dots are representing, is the attraction of one molecule to another. So the covalent bond between the two chlorines is the intramolecular force within the molecule. The intermolecular force is between, right, one molecule and another. For nonpolar molecules, that intermolecular force is just really weak compared to a polar molecule that has positive and negative ends. The positive end of one and the negative end of another allow it to attract much more strongly than one end of a chlorine molecule can attract to another chlorine end of another chlorine molecule. To explain this idea of why one molecule would be polar where one would be nonpolar, we had to look at the term electronegativity. And electronegativity is an atom's ability to attract electrons towards itself. And every atom does it to a different degree. So fluorine, we saw in class, has the highest electronegativity, where francium has the lowest. Now, the noble gases have no electronegativity, right? That's because the way we measure electronegativity, the real technical definition is an atom's ability to attract electrons in a chemical bond. Well, the noble gases we know are stable on their own. They don't bond, so we can't get electronegativity data for them, so it's sort of a moot point. Francium does bond, so of all the elements that bond, francium has the lowest electronegativity. So we see this upward trend to the right in terms of increasing electronegativity. Now, what does this actually mean? Well, this means if I look at two atoms that are bonding, let's say hydrogen to hydrogen, right? They're forming a single covalent bond. Because each hydrogen atom has the same electronegativity, meaning they can pull on those two electrons with the same strength, effectively the electrons go nowhere. If you think of it like a tug of war, the electrons stay exactly in between the two hydrogen atoms, and that means they will not make one end of the bond more negative, right? So that's a nonpolar bond. We're looking at the electrons in between two atoms, and are the electrons being shared equally or not? This is different than whether the molecule is polar or nonpolar. That's looking at the overall shape and whether one end of the molecule will be positive or negative. What we're looking at is the bond, so just the pairs of electrons now and how they are being shared. It's a really important difference. So in the case of the two hydrogens, they will form a nonpolar covalent bond because they share the electrons equally, because they have the same electronegativity value, the same pull for those electrons. But if I look at a HCl bond, still a single covalent bond, what I notice is that chlorine pulls the two electrons closer to itself. Why? Because chlorine's electronegativity value is greater than hydrogen. So it has a better attraction for those two electrons than hydrogen does, so it is winning the tug of war. The consequence of that is that the electrons are being pulled more towards chlorine now, so the chlorine end of that bond is more negative than the hydrogen end. And we use the term dipole and that symbol to represent if the electrons are being pulled towards one atom over another, we use the arrow to show which direction those electrons are being moved to. So if we just summarize the types of bonds we can have, a nonpolar covalent bond is where the atoms are sharing electrons equally, meaning the two atoms have the same electronegativity. If we start to have a difference in electronegativity, where one atom is one strength and one atom is another, then the electrons start to shift towards the atom with the higher electronegativity because it has more control over that pair of electrons. That would be a polar covalent bond, like HF. Now, if the difference in electronegativity becomes so great, then there's really no shot at the atoms sharing electrons anymore. Then we have a transfer of electrons, and we're back to where we started in chapter 4 with ionic bonding. So we get an ionic bond by looking at two atoms where the electronegativity difference is so great that they can't even share. One atom that has the higher electronegativity completely rips the electrons away from another. We have a transfer of electrons, we form ions, and those two ions will bond ionically to each other. I gave us some summary information at the bottom here, so we can see how those three bonds are related. Again, nonpolar covalent here, where the difference in electronegativity, remember we use this delta En. We subtracted the electronegativities from each other to look at how great of a difference there is. If the difference is 0, we have a nonpolar covalent bond. Once we start to have a minimal difference, the electron cloud shifts towards one atom over the other. That creates one end that's negative and one end that's positive of the bond. But if the difference is so great, the atoms are not going to share. They're going to transfer electrons with one atom pulling electrons away from another, and we get two ions to form. So how does all of this relate to an entire molecule being polar or nonpolar? If we're looking at polarity of a bond, the question is, are the electrons being shared equally or not? If we're looking at an entire molecule being polar, we're asking the question, are the electrons in the entire molecule being pushed or pulled towards one end of the entire molecule, not just one individual bond? So what we have to do here is look at the individual polar bonds and see, do they cancel each other out around a central atom or do they not? So as an example, in CF4, which is a nonpolar molecule, I do have polar bonds. We can look, see the 4 dipoles here. So each of the fluorines is partially negative, where the carbon is partially positive. I have 4 identical polar bonds, but the fact that they're identical, the fact that the shape is tetrahedral allows those identical dipoles to cancel each other. There is no one end of that molecule that is more positive or more negative than another. So this is a nonpolar molecule. Where in CHF3, I still have 4 polar bonds. 3 of them are identical. 1 of them is different. And if I look, I can see that the net movement of electrons is from the hydrogen to the carbon, and then from the carbon to these outer fluorines. So this net dipole, which you can see drawn in gray here, I'll highlight it in blue, shows that the electrons are being moved towards this end and away from this end, which makes this end more negative, that end more positive. That creates a polar molecule. Water is a famous polar molecule. Its bent shape and its 2 polar bonds show that the net movement of electrons is up towards the oxygen. That's why this end is more negative and this end is more positive. So we have to look at the shape of the molecule and whether or not the polar bonds, if they exist, cancel or not. HCl, right, a linear molecule that's polar because the chlorine is pulling the electrons more towards itself than the hydrogen. We went over the fact that water is polar. BF3 is nonpolar. It's a trigonal planar molecule. And the boron-fluorine bonds are all identical. So although they are polar towards the fluorine, they're pulling equal and opposite each other. So their effect of pulling the electrons away from the boron basically cancels each other out. NH3 is a trigonal pyramidal molecule. And because of the lone pair, because of the asymmetrical shape, you would think it might look like BF3, but it's not flat. So the nitrogen-hydrogen polar bonds don't cancel each other out. There's a net movement of electrons upward, right? Each nitrogen's pulling up this way, and then one behind. So there's a movement of the electrons up towards the top of the nitrogen, making this end partially negative and this end partially positive. And then, again, the examples of the tetrahedral molecule were like the examples up here, so I won't go over those again. But the idea here is that only 2 shapes we looked at were always going to be polar, bent and trigonal pyramid. Every other shape we looked at, linear, trigonal, planar, tetrahedral, could be either polar or nonpolar depending on if the molecule was symmetric, right? The dipoles around the central atom need to be symmetric. They need to cancel if the overall molecule is going to be nonpolar. And that's what the X's and Y's here are showing. In this case, we have a tetrahedral molecule with the surrounding terminal atoms are the same. So all of the dipoles are the same, so they all cancel each other out, right? They're symmetric around the central atom. Where in this tetrahedral, I have one terminal atom that's different from the others. And as long as one is different, the dipoles are not going to cancel each other out, so there's going to be a polar molecule. The negative end of the molecule, or the partial negative end, right? That idea, this symbol, that delta, was partial. It's not a full positive or negative like in an ion. We're not completely losing or gaining charge. The charge is shifting towards one end or the other. The end of the molecule that's going to be partially negative is going to be the one whose atom is the most electronegative. So you can always use the electronegativity rules there. The last little bit we looked at was relating the idea of whether or not a molecule is polar or nonpolar to whether it smells. And the molecules that are polar, I'm going to use PCl3 in the plate example over here. PCl3, based on its electron domains, is a trigonal pyramidal molecule. So it looks something like this. And if we look at the electronegativity, we can go back to this table because we have it. Chlorine is 3.16, phosphorus is 2.19, so chlorine has the higher electronegativity, meaning that the net dipole is in this direction for this molecule. This is partially positive, where this is partially negative. And that means if we threw that one molecule in this electromagnetic field with these plates here, the partial positive end, which is the phosphorus, is going to align itself with the negative plate, and the partial negative end, which is going to be the ends with the chlorines, is going to align itself with the positive plate. Now, taking that into consideration, we looked at the receptor site theory. If a molecule in the gaseous phase is going to get to our receptor site, it has to dissolve through the mucous membrane. Mucus is made of mostly water. Water is polar, and we know like dissolves like. So, polar molecules are going to be the ones that are more likely to dissolve through the mucous membrane because they are polar like water, and like dissolves like. They will be able to align their intermolecular forces to dissolve in that mucous membrane. Once they get through the mucous membrane and get to a receptor site, the receptor sites are made of proteins that are polar molecules themselves. So when we say that the molecule docks or attaches, what it's actually doing is it's aligning its positive or negative end with the positive and negative end of the receptor site, and they are attracting via intermolecular forces in that way. So even if a nonpolar molecule did get through our mucous membrane, the chances of it being able to attach to a receptor site is really low because nonpolar molecules don't have positive or negative ends to attract itself to the partial positive and negative ends of the receptor sites. So once we understood the idea that polar molecules are more likely to smell than nonpolar, and for the various reasons we went over and I just explained again, we wanted to take one final sort of pass at everything we've looked at so far in the smell unit, and then even related to some of the stuff that we saw in the alchemy unit, specifically bonding. So based on type of substance, how the atoms are put together, meaning how they are bonded, I'm going to start down here. Metallic substances have no shot at having a smell because all metals, with the exception of mercury, are solids. And even though mercury is a liquid, the atoms are still too strongly attracted to each other where they're not readily turning into vapor. Even for solid metals, not readily turning into vapor. So no shot at them having a smell. Although we think metals smell, we talked in class that it's actually, they only smell when we touch them, and it's because the metal's reacting with the oils on our skin to produce a separate molecule that has a smell. Ionic compounds, for the same reason as metals, no shot at smelling because every single ionic compound at room temperature is a solid, and the ions are too strongly attracted to start turning into a gas at room temperature. Molecular covalent compounds are the only type of substances that could possibly have a smell, but it depends on a couple of things. One is size. The large molecular covalent compounds don't have a smell because their intermolecular forces are too strong. So the molecules are being held together very tightly, meaning the phase of matter for large molecular substances is a solid, and they're not readily turning into a gas at room temperature. Small molecules could have a smell, but not if they're nonpolar. For reasons we explained before, nonpolar molecules can't dissolve through the mucous membrane and they can't attach to a receptor site. So the only two types of molecular covalent compounds that could potentially have a smell would be small polar molecules, because they dissolve through the receptor site and attach to the mucous membrane, and medium-sized molecules, both polar and nonpolar, interestingly enough. Polar, we could explain, is the same reason for small polar molecules. Nonpolar molecules, if they are medium-sized, fall into this weird gray area, where although they're nonpolar, the larger the molecule gets, the more polar it can act. And the more electrons a molecule has, the more random fluctuation of those electrons in the molecule. They can develop partial and positive negative ends for really small amounts of time, and that's what the medium-sized nonpolar covalent molecules can do. Medium-sized molecules, because of the medium strength of the IMFs, will mostly be liquids. The small molecules tend to be gases. But we summarized, based on the type of bonding, that network covalent, right? That was the strongest type of bonding. That's why I wasn't even in this chart here. No shot at smelling. Metallic substances, no shot at smelling. Ionic substances, no shot at smelling. Molecular covalent, yes, but we have to ask two questions. One, is it polar or nonpolar? And two, what is the size of the molecule, right? And we should probably ask about the size first. If it's a large molecule, no shot. If it's a small molecule, then yes, but only if it's polar. If it's a medium molecule, then yes, whether it's polar or nonpolar. That brings us to the end of Chapter 8 and the end of Unit 2.